Hi guys, and welcome back to my channel. In this video we're going to be talking about real gases. So in the previous videos we've discussed extensively about ideal gases and the sort of assumptions we make that comes from the kinetic molecular theory, right? But obviously that's just a theory and those are assumptions we are making, right? Real gases under certain conditions don't actually act according to these assumptions, right? So for example, we made the assumption that the volume of the particles themselves are negligible or that there are no intermolecular forces. We know that all of these sort of assumptions aren't actually completely true, and in certain situations these assumptions are really not going to be true, and they're gonna create we're going to predict inaccurate things because of these assumptions. So by discussing real gases and some of the properties that real gases have, we'll be able to understand how actual gases work in actual environments. So on this slide, I just want to discuss why we're correcting, the ideal gas law, what exactly is wrong with it. And as I said in the previous slide, the big fault of ideal gas law is that it relies on kinetic molecular theory, and kinetic molecular theory has several assumptions that are, not very accurate in certain situations. So what are the two things that are really never true exactly with kinetic molecular theory? Is that kinetic molecular theory assumes that gas particles themselves have zero volume and there's no interactions between particles. And these two things are false, right? Gas particles do have a finite volume, right, at all times, and particles do interact with each other through intermolecular forces, right? But we assume in kinetic molecular theory that the IMFs are really, really weak, that we can basically say that they're zero, and that the gas particles are really, really small, that we can basically say that their volume is zero. But this is not always true. But as pressure goes to zero, right, as pressure gets really, really small, that's when kinetic molecular theory is really, really accurate, right? And because these assumptions are basically valid. So let's talk about that. When the pressure gets really, really small, volume gets really big, right? And when volume gets really big, the volume of the gas particles themselves are negligible. Because comparatively, right, if I think about the volume of the entire gas itself versus the volume of the tiny gas particles, comparatively, as the volume gets bigger, the gas particles add, basically no volume to the volume itself. So you got to think about comparative volumes, right? The gas particles themselves have such small volume that when the volume of the gas itself gets very big, it basically doesn't matter. Also, intermolecular forces are negligible when the volume gets really big, because as volume gets big, gas particles get farther apart, and when the gas particles are farther apart, there is less, force in between them, less attractions between them. So our entire goal in this video is to correct the faults of the ideal gas law. And here I just wanted to show a little potential energy diagram, so you should have sort of seen this before. And what do we assume with kinetic molecular theory? With kinetic molecular theory, we assume that no matter how far apart particles are, right, no matter what the separation is, all these particles have the same potential. There's no intermolecular forces between them. So if this was a graph, of kinetic molecular theory, we would sort of have a flatlining potential. No matter the separation between these sort of particles, there's no IMFs between them, so there's no force between them, so the potential doesn't change, right? Okay, but in reality, there's sort of this sweet spot separation, right? If the atoms get really close to each other, if the particles get really close together, the potential gets really high, right? Why? Because there's a large repulsive force due to the particles overlapping electron clouds. But when the particles are really far apart, the potential also gets higher. Why? Because there's an attractive force between these particles. So the particles want to get closer together because they have intermolecular forces. So this is a potential diagram that we've seen many times and it'll keep coming up, right? But I just wanted to show our assumption is that there's a flat line, but this is obviously not true, especially when we have to look at gas particles that are sort of close to each other and therefore have intermolecular forces that are not negligible. So now in the following slides, I want to introduce some ideas on how we can fix the ideal gas law. The first idea I want to introduce is the notion of a compression factor, which we denote with the letter Z. We define compression factor as the V molar of a gas, the actual V molar of a gas, divided by the V molar that we would calculate using the ideal gas law. And essentially what this compression factor is going to do is account for intermolecular forces of a gas in a semi-quantitative sort of manner. So let's look at three sort of main cases. Say we have an ideal gas. That means that the V molar of the gas is equal to the V molar of that we would calculate using the ideal gas law, because that's the definition of an ideal gas, right? So our numerator and denominator are going to be equal. So we have a Z equal to 1. And that is the assumption, and the assumption we're making there is that there are no intermolecular forces, there's no sort of interactions between gas particles, right? So we're going to think about everything in comparison to this. So say we have, a two-particle system. I'm just going to draw this for simplicity. This is our ideal gas, right? There's no interactions between this, so it takes up a certain volume. Now let's look at if there's repulsive forces dominant, right? Our V molar is going to be greater than the ideal gas molar volume. Why? Because these two particles that I've drawn, see this for this ideal gas system, are going to push away from each other. There's going to be repulsive forces, so they're going to go farther apart, right? So the actual molar volume is going to be greater than the one we've calculated using the ideal gas law, which is what I've drawn in the first picture, right above. So the V molar is going to be greater than the V molar ideal, and that gives us a Z greater than 1. Repulsive forces are dominant, Z is greater than 1. And now we can think about the same thing if we have attractive forces dominant, and I'll draw this again really above next to the ideal gas. So we have, this is our ideal gas. Now there's some attractive forces, so these guys are going to get pushed closer together. And our V molar is going to be less than our V molar of an ideal gas because now there's attractive forces that are going to pull these particles together. And this is the case for the majority of gases, right? Majority of intermolecular forces are pulling particles together. So when attractive forces are dominant, Z is less than 1 because our V molar is less than the ideal gas V molar. And we can use this Z factor to sort of correct our ideal gas equation to look like this. PV equals Z times nRT. And how I like to rearrange this is that the actual volume equals, or V molar equals RT over P times Z, right? I divided by the molar, the moles on both sides, and I moved the equation around. And Z, remember, is just V molar over V molar ideal. And this term, this RT over P, is what is the V molar ideal. So this will end up canceling the V molar ideal on the denominator, and we get V molar equals V molar, right? So that's how we can sort of correct this ideal gas law equation using the compression factor, but the compression factor actually needs to be sort of obtained, right? We don't know the compression factor, we need to experimentally determine it. So now I want to look at this graph over here on the right, and this shows the compression factors for many, many different sort of gases. We see ammonia, we see methane, we see hydrogen, you see all these different gases, right? And we also see an ideal gas as a reference. So, and it graphs the compression factor versus the pressure, right? So first we can look at what our ideal gas is, right? Our ideal gas has a compression factor of 1.0, right? That makes sense because V molar over V mol is going to equal V molar ideal for an ideal gas. And so we're going to have Z equals 1. And remember, our assumption is that no matter what the pressure is, we don't see anything changing with pressure. There's just no interactions, right? So our compression factor is always 1. But for real gases, you can see that this is obviously not the case, right? So let's look at most gases have Z greater than 1 only at high pressures. So now we're going to look at the case where we actually have real gases, which is hydrogen, methane. C2H4, ammonia, all of these sort of actual gases. And you can see that when we look at the graphs, right, most of these graphs are only passing z equals 1, right, becoming bigger than that, at these sort of really high pressures. So why is that? Remember, z is greater than 1 means that repulsive forces are dominant, right? So at high pressures, this sort of makes sense because your particles are getting shoved really close to each other because there's such a high pressure, to the point where their electron clouds are starting to overlap, right? So there's going to be very high repulsive forces. If you remember sort of like the potential energy diagram, when these things get really close to each other, it's a very high potential, which causes, a repulsive force. At lower pressures, attractive forces are generally dominant, right? Because at lower pressures, you have more normal systems, and you have these attractive forces that just come from intermolecular forces. But one important sort of interesting thing to notice is that if we look at hydrogen specifically, you see that unlike the other gases which dip below 1, right? You see all these other gases dipping below 1 and then becoming greater than 1 eventually. Hydrogen only has z greater than 1 at all pressures, right? And this is due to the attractive forces of hydrogen actually being really, really weak. Because hydrogen only has 2 valence electrons, right? If we think about the Lewis structure of hydrogen, we only have 2 valence electrons in the sort of bond, 2 bonding electrons, right? And because there's so few valence electrons, the polarizability of hydrogen is very, very low. Because more electrons implies that the molecule will be more polarizable, and therefore because it's so not polarizable, the London dispersion forces between hydrogen molecules are so weak that attractive forces are never actually dominant, right? Basically, the IMFs between hydrogen molecules are so weak that attractive forces are never dominant, and repulsive forces are actually always dominant. So that's an interesting thing to note from this graph of compression factors. Okay, so now I want to talk about a really sort of important effect of real gases that can be used to liquefy gases, right? And this is actually used in industry to liquefy gases. So what is the Joule-Thomson effect? The effect I'm talking about is the Joule-Thomson effect. And basically this effect says that a real gas where attractive forces are dominant, cools when it expands. And this makes sense, right? Think about a gas like sort of rapidly escaping and expanding into a bigger volume. It's going to lose energy, right? It's going to lose energy because there's attractive forces between these molecules, right? And when these molecules are all expanding, they're pushing against the attractive forces. Attractive forces want the particles to come together. Instead, they're expanding and going farther apart. We're pushing against it. We're losing energy, right? The particles are going to lose energy, and that's going to make the gas cool down because it's losing energy, right? So that's essentially what it's doing. We're pushing, the gas particles are pushing against the force, and they are losing energy. So the specific definition of the Joule-Thomson effect is the temperature change of a gas that is forced through a valve rapidly, known as a throttling process. So this is sort of the more technical definition, but basically it's the same idea as in the first bullet point. We're sort of forcing it through a valve rapidly, which means that it's expanding very rapidly, and that results in something called an adiabatic process. And an adiabatic process you should have sort of heard about from a Gen Chem course, but an adiabatic process just means that the heat transfer is equal to 0, right? And that's because this sort of escape of the gas into a bigger volume happens so rapidly. It happens so rapidly that there's no time for heat to be transferred, so Q equals 0, right? And we're looking at the temperature change of this gas, so that's sort of referencing the cooling as we're expanding. And the second point is what I stated at the beginning. Gases can be liquefied using this effect, and this is sort of why it's sort of important in actual industrial applications, is because you can sort of force gases and expand them, and they cool so much that they end up condensing, right? And so that's how you can actually produce certain, liquid gases, or things that are normally gases and turn them into a liquid. Okay, and the next sort of important key point is that the Joule-Thomson effect is isenthalpic. And that means that the enthalpy change of the Joule-Thomson effect before and after is equal to 0. And we're going to talk much more about sort of thermo in future videos, but I just wanted to introduce this terminology, right? I want to introduce some key terminology from thermodynamics in this video, and we'll go into much more depth later on. So this is a little bit optional because we're going to go into much more depth on these terms and, internal energy, enthalpy, entropy, all of these sort of ideas later on in this Atkins lecture series. And so we also define something called the Joule-Thomson coefficient. So we've sort of given this vague notion, right? Okay, real gas is going to cool when it expands. Cool. But how much does it cool when it expands? Like, how can we quantify this notion? How do we know which gases are going to cool, faster than others and cool less fast than others? And, how can we actually quantify this notion of cooling as it expands? That's what this Joule-Thomson coefficient sort of does for us, right? So this is going to formalize this sort of idea of cooling when we expand. And we define this as mu. We define this Joule-Thomson coefficient as the change in temperature with the change in pressure. So dT dP, right? How does the temperature change as pressure changes? Okay, so let's look at first ideal gas. We're going to look at the simplest cases, ideal gas. With an ideal gas, mu is equal to 0. So why is mu equal to 0? There's no intermolecular forces, right? There's no attractive or repulsive forces. So when we expand, the particles aren't actually losing any energy, right? Because I'm expanding, but I'm not pushing against any attractive force or being helped by any repulsive force. I'm basically just moving, right? And there's no sort of forces against or with me. So there's no sort of work done. I'm not losing any energy. I'm not gaining any energy, right? So the energy stays the same before and after, which means my change in temperature is going to be 0, right? So dT dP is telling me how does my temperature change with pressure. My pressure can do anything, right? If I expand, that means my pressure goes down, but my delta in temperature is 0, right? Because there's no attractive or repulsive forces I'm pushing against. So dT dP will just be 0 as well, because there's no change in temperature. Now let's look at attractive forces being dominant. And this is what happens for most real gases. Remember, attractive forces are generally dominant at normal sort of pressures, right? Only when we push at really, really high pressures and we have electron clouds overlapping is when our repulsive forces become dominant. So if we have dT dP, right, let's look at dT dP for attractive forces dominant. That means when I expand, gas expands, right? Gas expands, what happens? That means volume increases, right? Which means pressure is going down. Whenever volume increases, pressure is going down. And when I'm going against attractive forces, what happens? I cool, right? My gas is going to cool. So what does that mean? Pressure goes down, temperature goes down. That means temperature and pressure have a direct relationship, right? Temperature goes up, pressure goes up, temperature goes down, pressure goes down. Or technically it's the other way around. Pressure goes up, temperature goes up, pressure goes down, temperature goes down. Which means that dT dP, right, how is temperature changing with pressure, is going to be greater than 0. Mu is going to be greater than 0 because we have a direct relationship. If pressure increases, that means temperature is also going to increase, which means that mu, which is delta T over delta P, you can think about it as deltas, right? We don't need to introduce sort of calculus notation, but you can think delta T over delta P. If temperature increases or if pressure increases, that means temperature will also increase. So both the top and the bottom will be positive, which means that mu is going to be a positive number divided by another positive number, which gives you a positive number. So we have mu is greater than 0 for most real gases when attractive forces are dominant. Now if we look at repulsive forces dominant, we have a different situation, right? And this is generally key for small gases at lower temperatures, right? Lower temperatures means that the gas particles are closer together, we have more repulsive forces. Small gases also means that we have low polarizability, which means that attractive forces are very weak, which means that generally repulsive forces can dominate. If we think about repulsive forces dominating, when the gas expands, it's actually being helped by the force, right? Because your force is in the direction of the expansion, right? It wants to expand instead of it wanting to compress and attract each other. So what is actually going to happen? It's going to gain energy because the force is sort of pushing in the direction of expansion. So we're actually going to gain energy and the temperature is going to increase, which is kind of a weird notion to think about, right? Expansion is going to cause heating when we have repulsive forces that are dominant. So when we have volume increasing, that means that we have pressure decreasing. So we have the change in pressure is less than 0, implies that the change in temperature is greater than 0, which means that if I look at delta T over delta P, or dT/dP for our Joule-Thomson coefficient, we have a positive number divided by a negative number. So we have a negative Joule-Thomson coefficient, which is what I've written here. So basically, to summarize, mu equals 0 for ideal gases, mu is greater than 0 for most real gases where attractive forces are dominant, and mu is less than 0 for small gases at lower temperatures where repulsive forces are dominant. In the next slide, we're going to derive, I'm going to show why the Joule-Thomson effect is isenthalpic, and this is not super necessary for you to know, right now, but it'll be a good introduction to sort of the language of thermodynamics that we'll go into in future videos. Okay, so this is a proof of Joule-Thomson effect being isenthalpic. Basically, we're going to think about this as we start with gas in some container, and this container has a volume V1, right? We're going to treat it like gas particles in this volume, and we have a tiny little hole, and then we sort of push it, we throttle it rapidly to another gas container with a volume of V2. So essentially what we're doing is we have this gas in a volume of V1, and it also has a pressure of P1, and now what we do is we throttle it, right? We push it super fast through a tiny hole into a new volume that has a pressure of P2. And we're trying to figure out, what is the enthalpy change of this process, right? So first, we start with volume equals V1, so this is what I just said, and the gas is forced through a valve into another container, ending with volume equals V2. And P1 and P2 are the starting and ending pressures. So now I want to calculate the work that needs to be done for me to sort of push this gas from P1, from a state of pressure 1 and volume 1, to a state of pressure 2 and volume 2. And work is defined as integral P dV, right? You should know this formula from previous courses, right? So we can split this integral up into two sort of steps. The first step is compressing the gas to basically 0 volume. And then the next step is letting the gas expand into our final volume. So that's what I've done in this sort of integral where I've broken it down into two components. First, we have this compression from V1 to 0, right? I'm going from my initial volume to 0 volume, and my pressure is P1, so I have P1 dV. And then second step is I'm expanding from 0 volume to my final volume, V2, and in this case, my pressure is P2, right? That's my final volume, P2 dV. And when I do this integration, I get negative P1 V1 plus P2 V2. This is just taking the integral of these two integrals, right? Actually calculating it. Now we know from the first law of thermodynamics, right? We know that the change in internal energy, which is equal to the final internal energy minus the initial internal energy, is equal to the heat transfer minus the work done by the gas. What do we know about the heat transfer? This is an adiabatic process which means that there's no time for any heat to be transferred. So Q is equal to 0. So we basically have that this is equal to minus W. And if I take minus of this, what do I get? I get P1V1 minus P2V2, right? So remember, this is an adiabatic process, so Q is equal to 0. So this is my change in internal energy, just by doing the math, right? So I have U2 minus U1, which is my change in, that's my definition of sort of change of internal energy, is equal to P1V1 minus P2V2. And I can rearrange this by moving the U1 to that side and this guy to that side. And what do I get? I get that U1 plus P1V1 equals U2 plus P2V2. And U1 plus P1V1, this is defined as the enthalpy at our first state, right? Basically the enthalpy at the beginning. U plus PV is what enthalpy is defined as. So H is enthalpy is defined as U plus PV. So this is something we'll go over in later videos, but this is sort of an important definition to know in thermodynamics. So this left side is equal to the starting enthalpy. The right side is equal to the final enthalpy. So we've just shown that the starting enthalpy equals the final enthalpy, which means that the change in enthalpy is equal to 0, which means that my process, the Joule-Thomson effect, is isenthalpic. So this was a short little proof to show that the Joule-Thomson effect was isenthalpic, and this exact sort of derivation is not very useful, or is not super important, but just introducing this notion of work, how to calculate work, knowing what heat transfer is, knowing what work is, knowing what enthalpy is, will all be really important in future thermodynamics videos. Okay, so now I want to go back and talk about how to fix the ideal gas law. Remember how we talked about what did we talk about already? We talked about compression factors. Compression factors. And this was our sort of how we fixed, that was one sort of method we used to fix the ideal gas law. Another method we can use is called the virial equation. And this is actually not a super important method. It's more useful when you're doing, stuff with computers, but you're basically taking experimental data and molding the ideal gas law to fit that experimental data. And I'll show you what I mean by this. So this method is the most accurate method of describing real gases, but has very little physical intuition. So this is important. The coefficients in the virial equation have very little actual meaning. You're just fitting the data to the best of your ability. So it's not super important for, chemistry Olympiad or anything like that. It's more important when you have high, efficient computation devices. But I still wanted to introduce it and talk about it a little bit. So basically what we do is we assume that the ideal gas law is the most predominant term in a more complex expression. And this is how we write the virial equation. PV equals nRT, right, times, so we can see that this is sort of like the ideal gas law, times 1 plus some other terms, V molar plus da da da. So we're basically taking if you have had exposure to calculus, this is somewhat like a Taylor expansion, a Taylor series, and we're fitting these coefficients of the Taylor series as best as we can to sort of match experimental data. And I'm not really going to go into much depth on this, but the virial coefficients are determined by fitting the data to the equation, right? But one thing I want to note that is important here is that if we multiply this sort of out, our first term is PV equals nRT. And then we have plus another term, you know what I mean? So we have, but nRT is our first sort of term on our right side, the most predominant term. So that just shows, I wanted to show that the ideal gas law actually does sort of pop out of this, and we're just sort of adding new terms that have a smaller effect on the actual right side of the equation. but the main sort of predominant term is the nRT on the right side, which gives us our ideal gas law. Now, here's the really sort of important thing. If you take one thing out of this video, it should be the van der Waals equation. It's really, really important, and it's how we actually sort of intuitively can understand how real gases work, right? This is the most useful equation for describing real gases. So if you don't remember compression factor, you don't remember v-real equation, this is something you really, really should focus on remembering, right? So essentially, this is our equation. P plus, so this has a lot of coefficients, or it has two main coefficients, and it looks a little bit messy, but bear with me, I'll explain through what all of these coefficients and why they're there and what they mean, right? So we have P plus A over V molar squared times V molar minus B equals RT, right? And this is, and remember that the ideal gas law is PV molar equals RT, right? This comes directly from PV equals nRT. So we see some sort of differences, right? What are the two big differences we see? We see that there's a term added to our pressure, right? This P becomes P plus some A times, or A divided by V molar squared. And we have a term subtracted from our V molar. It's V molar minus B now, right? And our right side is basically unchanged, it's just RT. If I solve this equation, the van der Waals equation for pressure, we get this. That's what I boxed. P equals RT over V molar minus B minus A over V molar squared. Okay, so that's a lot of sort of information. Let's sort of break this down, right? What are each of these terms doing? So first of all, look at this minus A over V molar squared. Minus A over V molar squared. This is going to reduce the value of the pressure, reduce the calculated value of the pressure. This is because, right, why it's reducing the value of the pressure. This is because intermolecular forces are attractive, right? We have attractive IMFs in a real gas, and this is going to reduce the force at which gas particles collide with the container, right? Because these gas particles are going to be attracted to each other and are going to bounce off the actual container with less force because there's going to be a force that's pulling them towards each other. So this term is basically saying we're reducing the pressure because that is a result of attractive intermolecular forces. But why do we have V molar squared on the bottom, right? How does that impact sort of how much our pressure is going to be reduced? The lower the value of V molar, the more tightly packed together the gas particles are, and the more attractive the IMFs are going to be. So VMF, or the V molar, if the V molar is really small, right? If we have a small value, if we have a small molar volume, that means we have packed, very packed sort of particles, gas particles, right? Which means that IMFs are very strong, and we have a lower pressure, right? We have a decrease in pressure because the IMFs are going to increase, and that's going to reduce the pressure even more. So that's why we have this second term, right? This minus A over V molar squared. Now let's look at the other term, right? We have RT over V molar minus B. So let's look at specifically V molar minus B. Because normally if I solve for pressure, like if I look at ideal gas law, I would have pressure equals RT over V molar. But in this case, instead of RT over V molar, we have RT over V molar minus B. So why do we have that minus B term? V molar minus B tells us the actual amount of space the gas molecules can move around in. So this is the actual amount of space gas can move around in. So then what is B? B is a measure of how much volume a mole of the gas particles themselves actually take up, right? So B tells us, remember how we assumed that gas particles have no volume? B is telling us sort of a measure of how much volume the gas particles themselves are taking up. And another way we can think of B is remember how we thought about A as describing the attractive forces, IMFs. We can think of B as describing repulsive forces. B is basically describing the repulsive forces between particles that prevents one particle from occupying the same volume as another particle, right? So B is telling us that, okay, when I have a gas particle cannot be literally on top of another gas particle. It only has this amount of space to sort of go around in. That's describing repulsive forces, because the reason a gas particle cannot be in the same exact spot as another gas particle is because their electron clouds are going to overlap, and that's going to have huge repulsive forces. So in that way, A measures the strength of attractive IMFs, whereas B measures the volume of the gas molecules, or B also measures, in another way of thinking, the amount of repulsive forces between the gas molecules. So to clearly see how A and B sort of represent attractive and repulsive forces, we can look at the compression factor. So remember that Z equals PV over nRT. Z equals PV molar over RT. Z equals PV over nRT. Because if we remember from our previous slide, right, we had PV equals Z times nRT was our corrected ideal gas equation, right? So just moving this around, we have Z equals PV over nRT. Now I can plug in, right? We can then sub in the van der Waals expression for P. So we're taking this expression that we solved for pressure and subbing it in to our PV over nRT. And this is what we get, right? Basically, I'm taking RT over V molar minus B minus A over V molar squared times V over nRT. That's essentially what I'm doing. And we end up with this expression, right? Okay. And now if we separate this expression into two, we get that the Z is equal to V molar over V molar minus B minus this A over RT V molar term. So we have two terms, right? And now let's look at how A and B, how this compression factor is going to change in relation to A and B, right? The larger B is, so as B goes up, what happens? The greater Z is. Z is going to go up. Why? Because when B goes up, this denominator gets, right? This denominator gets big. The V molar minus B denominator gets big, or gets small, sorry. And V molar divided by a small number is going to make the compression factor get really large, right? So as B goes up, Z goes up. And remember what we said, when Z is high, repulsive forces dominate. Repulsive forces dominate. But now let's look at if A goes up, right? The larger A is, the bigger A is, the smaller Z is going to get, because we have this minus term, right? And A is on the numerator, so the bigger A is, the more we're subtracting off, which means that Z gets smaller. And when Z goes down, attractive forces dominate. And this is sort of one way of seeing how A represents attractive IMFs and B represents the sort of repulsive forces that comes from the constraint that gas molecules themselves have finite volume. Okay, so this is basically all I wanted to talk about in this video. I hope it was informative. I know it was a lot of new content, but I hope you got something out of it. Thank you guys so much for watching, and I'll see you in the next one.